In this video, we're going to go over the concept of stress transformation as part of strength of materials. In the class, we've covered stress basically from chapter 1, and we've gone through in chapter 8, we learned about combined loadings and how that can result in both normal stresses and shear stresses on an element. And now we're going to look at, if we know the stresses at a point on an object based on one set of axes, how can we figure out what the stress would be if we rotated those axes? Because if you think about it, for example, this element here has 60 megapascals of tension in the y direction, 80 megapascals of compression in the x direction, and it's got a shear stress of 40 megapascals, we're told. That's about an arbitrary set of axes that we've just decided on, x and y. So in this case, we're asked, what would the stresses be if instead of looking at it on these x and y, we looked at a plane that cut from A to B, inclined at an angle of 50 degrees. So to do that, there's a couple different ways we can do that. We're going to go through a number of those methods in this video. The first one we're going to start with is kind of the simplest and our fallback default method, which is basically equations of equilibrium. So if we have this element up here, like I've said, it's got tension in the y direction, compression in the x direction, and we're supposed to find the stress on this plane. So I've drawn that same element, a larger scale down here in the corner. So again, I've shown we've got 80 megapascals of compression coming into this side, and I've drawn a new free body diagram basically of just this corner over here, and because we're supposed to find what are the normal stresses and shear stresses on that inclined plane of AB. So this most basic method basically comes down to using equations of equilibrium. I've shown the magnitudes here, but one thing before we start writing out our actual equations of equilibrium, we need to remember that our equations of equilibrium are sums of forces. And what we're given here are stresses. This is 80 megapascals, 40 MPa, 40 MPa, and down here 60 megapascals. These are not forces, they're stresses. So those stresses need to be, if we're going to use equations of equilibrium where we're summing forces, we need to turn these stresses into forces. And as you recall, a stress is just a force per area, and we have stress. What we need to include in our equations for equilibrium would be the areas. And so we can think about that on a kind of theoretical basis. Let's pretend that we could see the third dimension of this block here. Let me kind of draw it again up off to the side here. So if we got this plane, really that plane is extending into the page, right? There would be the shaded area is the plane that has our unknown normal stress would be acting out of that plane, and our unknown shear stress would be acting along that plane. And then we'd have our 60 megapascals of tension coming down there, and we'd have our 80 megapascals of compression on there. So again, those are stresses. We need to multiply them by an area. So for this example, let's call this big shaded area here, the whole shaded area on our plane AB, let's call that area delta A, or we could just call it A if we wanted to for area. And knowing that that's A, given that we know that this angle down here is 50 degrees, we can also write the areas on the bottom. This area down here then would be the magnitude of that area on the bottom would be our delta A. And here we're looking at adjacent to the 50 degrees. So in that case, we could say, depends on how you want to say it, I would probably say cosine of our 50 degrees there, or you could do sine of 40, however you wanted to. So that area is delta A times cosine 50, and then this area, the one that the 80 megapascal acts over, would be sine of 50. So it would be delta A times sine of 50. Okay, so just kind of thinking through the areas, and we'll see once we start writing our actual equations of equilibrium that those delta A's will all cancel out. But what won't cancel out is this factor that we've put in there, the cosine 50 or the sine 50 here. So let's go ahead and add that information onto our free body diagram here. So again, we're going to call this, the force that's coming out here is going to be the sigma prime, our unknown normal force, times delta A. Same with our shear stress on that plane is going to be shear stress times the area to get us a force. So again, times delta A. And down here, these two are both on the bottom surface, which we said that's the adjacent angle here from 50. So it'd be 60 megapascals times delta A times cosine of 50. And up here will be 40 megapascals times delta A times cosine 50. So that's going to be the magnitude of that shear stress converted into a force on the bottom. This is the magnitude of the normal stress times area, so force on the bottom. This one's 80 megapascals times delta A. And this one we said it's the opposite from our 50-degree angle, so that would be sine of 50 degrees. That's the magnitude of that force. And this one would be 40 megapascals times delta A, also times sine of 50, because it's also acting on this face here. Okay, so we've now got the magnitudes of the forces, and like we said, we've got a delta A in each one of them, so once we start writing our equations of equilibrium, they'll actually cancel out. But let's think about writing our equations of equilibrium next. You'll recall that we'll typically start with our equations of equilibrium. Simplest one might be sum of forces in x or sum of forces in y. So here, as I've drawn it out, I have x being this direction, with positive x being to the right, and y being vertical. If you think about, if I just started saying sum of forces in x, I could do that, and this force would have no component in x. This one would be all in x. This one would be all in x. This one would have no x. It's all in y. But then both sigma prime and tau prime, they both have some component in x, right? So if I wrote sum of forces in x direction, I'd have an equation with two unknowns in it. And I could still solve that. I could write my sum of forces in y, and I would, again, each of these would have a y component. But then I'd have two fairly long equations that I'd have to solve simultaneously. So what we want to do on a problem like this is find a system of coordinates that makes more sense for us. And they've given us that this is 50 degrees here, so it probably makes sense to do our sum of forces along the unknown or along this rotated. And so they gave us 50 degrees coming up from this way. Another way of thinking that would be our x-axis. I mean, that's kind of like our another way of saying that, I guess, would be that our y-axis has rotated back 40 degrees, so our x-axis is rotated up 40 degrees. So let's draw on here just another set of axes to kind of help us keep clear of that. So if this is our original x-axis, let's create our new y-axis that'll be rotated up 40 degrees. So, I'm sorry, not our rotated y, it's x is rotated up to where this is now would be x prime. And let's say if we have this as our y-axis up here, it's going to rotate again 40 degrees in the same direction. So we'll go perpendicular to that one I just created. And this now is y prime. So now if we look at it, my unknown forces each act entirely in one of my new rotated axes. So that will make my sum of forces equations a little easier. On the other hand, now each of my known forces is going to have an x prime and y prime component. But those are known forces, so I can go ahead and calculate what those are fairly easily. So let's just draw those out to help us kind of think that through. Let's draw out the x prime component of each of our forces, and then we'll go back and do the y prime. So let's look at the 60 megapascals to start with. When we look at x prime, so we're looking at what component of this acts in the parallel direction to x prime. And we can see that it's going to be moving in the negative x prime direction parallel to that axis. So it's going to be something like that looks like. And while we're here, let's do the y prime part too. So again, now we're looking at parallel to my y prime axis, so it's going to be something like this. So it looks like I went way too far with the tail of that one. So it's really something like that. Okay. That looks good. And I guess while we're here, let's do the same thing for this one. So again, we're going to come down. There's the y prime part. And there's the x prime. Sorry about that in there. Just pretend that's not there. Okay, let's do it for these ones up here. So again, we can look at our y prime. So parallel to this, that would be this piece here. And an x prime parallel to this, so that's going to be there. Okay, and last one now. Let's do parallel to y prime. And then parallel to x prime. Okay, so now we have taken all our known forces, and let's just write in the angles to make that nice and clear for us there. So what's an easy one here? We can see that our angle here is 50 degrees, so we know this one's going to be, they're perpendicular, so this is 90, so this down here really is 40 degrees, and that's what we said, right? That the x-axis rotated up in our positive direction. And remember, how do we know what angle is a positive? We follow the right-hand rule. So if our fingers sweep from x to y, which they do like this, then that's the same direction that we consider positive for our angle of rotation. So this is a positive 40 degrees of rotation to get to our rotated axes here. So this one's 40, this one's 50. So then looking at alternate interior, this would be 50, 40, 40, 50. Same thing up here, we'd be at 40 and 50 and 40 and 50. Okay, so I think we can start writing out our equations of equilibrium now. So let's do our first one as sum of forces along x prime. And right and up being my positive sign convention. Okay, so let's just start out with my unknown force. I have, the way I've drawn it here, I've assumed a direction of up and to the right. We'll see once we finish the problem if that ends up being the correct assumption of direction. So I'm up and to the right, and so I'll call that positive sigma prime times its area would be delta A. Okay, that was the first nice easy one. Let's start looking at our other terms. So we're looking along x prime, so we're looking for the kind of fuchsia component of each of these. And so we'll start, why don't we start with we'll just start right up here. And it helps to kind of develop a pattern as you work through a problem like this and be consistent. So if I do this 80 megapascal portion first on sum of forces in x, when I get down to do sum of forces in y, I should do that force first too. And I'll talk about that more once we've got them laid out here, but it helps you keep track of the trig as you go along. Okay, so we want to represent the magnitude of this fuchsia part of this whole vector. So we'll start out with the magnitude of the whole vector. And is this part going to be positive when we're looking at our x prime? It is, so positive. And then the magnitude of the whole vector, that's 80 times delta A times sine of 50. So that's representing as if this whole piece was along the x prime axis, but it's not. It's really only this piece here. So then I need to multiply it times cosine of 40 degrees, because that's a 40-degree angle. That's my adjacent. So katoa, I'm using cosine adjacent, so cosine of 40. So that represents that one. Let's now move up to this one. And is it moving in the positive x prime or negative? And it's going positive, so I'm already out of room over here, so I'll move down. So next one is plus 40 times delta A times sine of 50. That's getting me the magnitude of this whole vector here. And now I'm looking for this piece up here, and that's going to be, if we're looking at the 40 degree, that's the opposite, so it would be sine, so times sine of 40. Okay, so we've accounted for those two, so let's move down now and do these two. So on this one, if we look at the normal force, the component of the normal force that's parallel to x prime, we can see it's going in the negative x prime direction. Its vector head is down here, so I'm going to do minus. Its magnitude is 60 times delta A times cosine 50. That's the magnitude of this whole piece. And now I'm looking for this piece here. And again, if I'm using the 40, it's going to be sine, because it's the opposite, times sine 40. Okay, now we've got that little piece right there. Last one is going to be here. That's a positive x prime direction. Magnitude is 40 times delta A times cosine 50. And now I'm looking here, that's adjacent to my 40 degree angles, so now I'm going to be back to cosine 40. And all of that plus this plus this plus this plus this has to equal 0. Okay, so I can just plug in all those values into my calculator now, so I'll go ahead and do that. And I guess before I plug that in, let's just take a look at, I'm saying I can plug those in because in my head I've already canceled out all the delta A's. But to make that clear why I'm saying that, think about I have my unknown force times delta A here, and then 4 other terms that all have a single delta A in them. If I'm solving for my unknown sigma prime, I would move these 4 terms all over to the other side of the equal sign. Then I could factor out the delta A from each term, and then I'd have some long equation on this side times delta A, and I'd have sigma prime times delta A on this side. So basically what I could do then mathematically is I'm multiplying both sides by 1 over delta A, and all the delta A's cancel out. Okay, so now that I clarified that, let's go ahead and plug in values for each of these 4 components. So 80 times sine of 50 times cosine of 40 plus 40 times sine of 50 times sine of 40 minus 60 times cosine 50 times sine of 40 plus 40 times cosine 50 times cosine 40. And I get 61.548 basically. And I plugged that in all on this side where I hadn't moved it over to the other side of the equal sign yet. So really what that tells me is that sigma prime is equal to negative 61.548 megapascals. So again, just to clarify, if I plugged all those 4 terms in, I get a positive 61.547, but I need to move them to the other side of the equal sign, so that gets me a negative 61.548 megapascals. So what's that negative sign tell me? That tells me that when I assumed that the normal force, the unknown normal force, was moving away from the plane that I cared about, I was wrong. So I showed it as a tensile normal force. It turns out it's a compressive normal force. So I'll just write in here sigma prime equals 61.548 megapascals compression. Okay, so we've finished for that one. Now let's do it for the unknown tau prime parallel to plane AB. So again, it'll be equations of equilibrium. So I'll just do sum of forces in the y prime direction, which up and to the left being positive. Okay, so we'll start out with our unknown. That would be tau prime times delta A, and this is our positive y prime, so that's positive sense. Let's start working our way down through our known forces. And again, like I mentioned when we were doing sum of forces in x prime, I want to do them in the same order here, because if I do, that will help me look back and just catch any maybe copying errors I might have made as I went through. So, okay, we're starting with 80 mega, this one here. When I look at the y prime, that would be negative, so because it's moving down and to the right instead of up and to the left. So I'm starting out with a negative 80 times delta A times sine of 50. That just gets me the magnitude of this one. And now I want to get the piece of that that's moving parallel to y prime. So in this case, that would be the opposite from the 40-degree angle that I'm working with. And I could have done all these using 50s from the other side, but I just chose to use the 40. So we'll say sine of 40, because it's opposite from the 40. And this is why I was saying this is a good way to write it out like this so I can check each one. I can look back up. Was I cosine of 40 up here? Yep, then it makes sense that I'm sine of 40 here, because before I was looking at the angle or the component parallel to x prime. Now I'm looking at the component parallel to y prime. So I should be using the opposite trig function. Okay, let's move on to the next one we did, which was the shear stress up here. And the magnitude of that, well, first let's look at the sign of it. It's going up and to the left, so it's positive. Its magnitude is 40 times delta A times sine of 50. That doesn't change because that's still the whole magnitude of this vector. But now I'm looking at, before I was looking at the piece of it parallel to x prime. Now I'm looking at the piece of it parallel to y prime. So that's adjacent to my 40, so that's going to be cosine 40. Okay, moving on, the next one we did was the 60. So coming down here, looking at the piece of it that's parallel to y prime, looks like that's negative. So minus its magnitude, 60 times delta A times cosine of 50. And now I'm looking at the piece parallel to y prime. So that's here. So that would be adjacent to the 40 degree. So cosine 40. Last one, the shear stress on the bottom, that was magnitude. Well, let's look at direction first. It also will be negative because it's moving down and to the right. So minus 40 times delta A times cosine of 50. And now I'm looking at this part here. So that was opposite from the 40, so sine of 40. And all that's going to equal 0. Okay, and here again is where I was saying a nice way to check that I didn't copy anything down right. Looking at the magnitudes, they should be the same whether I'm looking at sum of forces in x prime or y prime, because those are the total vectors. So I should see 80, 40, 60, 40, 80, 40, 60, 40, and then I should see sine 50 times 2 times cosine 50. And yep, that's the same. Okay, and then when I look at the trig functions to give me the components along my rotated x prime and y prime, those should be opposite from the top set to the bottom. So cosine 40, sine 40. Yep. Sine 40, cosine 40. Sine 40, cosine 40, cosine 40, sine 40. So they're all opposite. So that's just a nice quick check to see if I made any mistakes there. So let's plug in values for that. So negative 80 times sine 50 times sine 40 plus 40 times sine 50 times cosine 40 minus 60 times, oh, I missed some parentheses there. Okay, minus 60 times cosine 50 times cosine 40 minus 40 times cosine 50 times sine 40. And I get all of that is equal to negative 61.99. But again, since really it needs to go to the other side of the equal sign, what that means is that tau x prime y prime would be equal to 61.991 megapascals. And the sign is positive. Once I get it over that sign, so that means the direction I'm showing it here is correct. So I think that answers everything we were supposed to find out. We were supposed to find the state of stress on the inclined plane AB. I didn't actually write that out here. On inclined plane AB. Okay, so answers would be sigma prime equals, if we were to go into 3 sig figs, that'd be 61.5 megapascals compression, and tau x prime y prime is equal to basically 62.0 megapascals. So we went through the process of finding the state of stress on the plane AB by using equations of equilibrium in a free body diagram. But as you saw, that's pretty tedious to draw the free body diagram, do all the trig to translate each known force into its components parallel to the rotated axes. So we've developed these stress transformation equations that are basically, if we take the free body diagram of that triangular inclined piece that we just used to solve and do the general solution of that using trig identities, we can come up with these equations here that show us the that we can just plug in the values for them. But before we go ahead and just plug those numbers in, it's important to review our sign convention about what is a positive, what is a negative, how do we talk about the sense of the forces and the angles, etc. So we have our same little element here that's got 80 megapascals of compressive normal force on the x-axis, 60 megapascals of tensile normal force on the y-axis, and 40 megapascals of shear stress. Okay, so let's talk about sign conventions of the forces first. You'll recall that anything that's moving outward on the x direction, we consider that a positive normal. And so that would be tension moving in the positive x would be positive. Same thing in the y direction. If it's moving upwards along our positive y-axis, that's going to be a positive force. Whereas if it's inwards or down on the top y-axis, that would be negative. So in our case here, we have, let's write out, we would have our sigma x, our normal force or normal stress in the x-axis. It's to the left or inwards to the element, so that's going to be equal to negative 80 megapascals because it's compressive. Our sigma y is moving in the positive y direction, so that's going to be positive 60 megapascals. And lastly, the shear stress, and this is the one that you just kind of got to remember. We're always looking in this quadrant of the positive x and positive y. If the shear stress is moving in positive y, that would be like that, and in positive x, that would be like that, then it's positive shear. You can see in our case, that's not the case. We have negative y, and then it's like this. So that is the negative shear. So in this case, our tau xy would be equal to negative 40 megapascals. Okay, so that's our stress sign convention, but we also have to remember our angle sign convention. So in this case, we were asked to find the stress on a plane AB that's rotated from the left 50 degrees, or another way of thinking of that, as we drew before, if this is our x, if it's 50 degrees there, that means that this angle would be 40 degrees. So we're swinging up from our x to x prime, and I can't remember what color did we use for x prime before. Was that fuchsia, I think? So this would be somewhere in there. That would be x prime, and then y prime would be perpendicular to that. It's going to be something like there. And this angle then, this is theta. And theta is positive if it's following our right-hand rule for the x and y axes. So remember, right-hand rule, fingers curve from x to y, and if the angle is moving in that direction, that's positive theta. So this would be positive theta. If, on the other hand, say they had asked us to rotate the other direction, and our x prime was down here, just make it noticeably a different angle so we're not confused. If this was x prime, then this angle would be negative theta. Okay, I think that's probably good for reviewing our sign convention. So now that we have those values established from our sign convention, we can just plug them in. So the equation defines stress on a rotated x prime, normal stress, perpendicular to that would be sigma x plus sigma y over 2. So that's, in this case, sigma x prime is going to be equal to sigma x, we said was negative 80, plus sigma y is 60, so plus 60 divided by 2, and then plus sigma x, negative 80, minus sigma y, so minus 60, divided by 2, times cosine of 2 times the angle, which in this case, the angle is between x and x prime, so that's our 40 degrees, times 40. And then plus tau x, we're actually putting a number in for it now. So tau xy, which was negative 40, times sine of 2 theta. So that's 2 times 40. Okay, so let's plug in values for all of that. And you can see we've got a couple terms here, and I usually just, to keep track of them as I'm going along, I'll just write each one beneath it so I don't make an error in a long calculation and have to redo the whole thing. So negative 80 plus 60, we could probably do this one in our head, but we'll do it. So we get negative 10, and then plus the result of this one, which is negative 80 minus 60 divided by 2, times cosine of 2 times 40. That's negative 12.1554 plus negative 40 times sine of 2 times 40. That is negative 39.392. So all of that added together is minus 12.1554 minus 10. So we get negative 61.548 megapascals. So sigma x prime equals 61.5 megapascals. And the negative sign says it's in compression. I think, hopefully that's the same thing we got before. Doing the method using our equations of equilibrium, yeah, we got 61.548 megapascals compression. So you can see it's much quicker to just plug them into our general equations for stress transformation. So we can do the same thing now for the shear stress. Tau x prime y prime is equal to negative. That's a common one I often forget to put in there when I'm working on these problems. Always remember there's that negative sign in front of it there. Minus sigma x, so sigma x was a negative 80, minus sigma y, which was 60, divided by 2, times sine of 2 times 40. Okay, and that one we'll just plug everything in. Negative 80 minus 60 divided by 2. Oh, I forgot the last part of the equation there. Plus tau xy. So plus a negative 40 times cosine of 2 theta. Sorry about that. I skipped on without writing that down there. Okay, so let me start over there just so I don't forget where I was, negative 80 minus 60 divided by 2 times sine of 2 times 40. Okay, so that's a negative of negative 68.937. And now the next term is plus negative 40 times cosine of 2 times 40. So that's negative 6.946 basically. Okay, so this one's going to end up positive. So if I add 68.937, I get tau x prime y prime is equal to 61.991 megapascals, or that's 62.0 megapascals. And I think if we go back and look again, that's what we had, yeah, using the free body method as well. So sorry, let me move up there so you can see that last little bit. So either method, we come up with the same answers, but this one's much quicker to just use our general equations for stress transformation. And you'll see I wrote up here the equation for sigma y prime, and we actually don't need to use that one in this case because we're only looking at the stress on the AB plane. If instead we were looking at the stress rotated 90 degrees from that, if we had cut the plane to be a triangle like this, then I would use the sigma y1, or if I was looking for the stress up a normal stress to that plane, I would swap which one I was using. So we've looked at the same problem two different ways now, first using equations of equilibrium and then using our general stress transformation equations. And those were both useful if we were asked to find the stresses on some oriented set of axes different than the ones we were given. And so you can get the idea. You could find stresses at any arbitrary orientation, but some orientations are more important than others. And one of the most important ones is what we call the principal stress orientation. And this is the rotation of an element such that it maximizes the normal stresses. And if you think about it, as you rotate each element here, some component of the normal stress in X and Y and shear stresses all add up. If we go back and look at this version, right? As you keep rotating this, the interplay between normal stresses and shear stresses, in one orientation, the normal stresses might be more and more and more, and then it starts getting less and the shear stress starts building. So there's two different cases that we really care about. And one is called the principal stresses, where our normal stresses are maximum. And when that's the case, our shear stress will be zero, because a way of thinking about it is that all of the stress in the object is oriented along normal planes at 90 degrees to each other when you're at the orientation of principal stresses. If you rotate from that location of principal stresses, if you rotate 90 degrees away from that, you will get, well, I'm sorry, if you'll rotate 45 degrees in the real world from that, you'll get to the maximum shear stress, 90 degrees on Mohr's circle, which we'll talk about more in a little while. But the key idea there is when you're at max normal stress, your shear stress is at zero. When you're at max shear stress, your normal stress will be average, which means normal in X and normal in Y will be equal to each other. So they're not zero, but they're equal in X and Y. And we'll look at that again more when we do the Mohr circle. That all becomes really clear. And as I've talked about in class, Mohr's circle is kind of the culmination of all of what we're doing here. It combines the ability to find stress on any particular plane, to find the principal stresses, to find max in-plane shear stress. It just brings it all together, but we kind of work through these steps to get there. So the next step we're on right now, after doing our equations of equilibrium method and then our general stress transformation method, is now we're going to look at the equations for principal stresses and for max in-plane shear stress. So we'll keep using the same problem as an example that we've been working with. So again, we got 80 megapascals of compressive normal stress in the x-axis, 60 megapascals tensile stress in the y-axis, and 40 megapascals of shear. And the shear is oriented in such a way that we would call that negative shear because it's not moving up and to the right there. Okay, so you can look to your text or recall from in class about the derivation of these equations. Basically what we do to come up with these equations is if we come back to our general equation for stress about any rotated x-axis, if we take the derivative of this equation and set it equal to 0, that's how we come up with these equations, one of which, this one here, tells us the angle, how much we need to rotate. Remember we had our definition of what a positive rotation angle was up here. We can use this equation here, tan of 2 times our unknown theta p. That theta p is the angle we need to rotate our element to get to the orientation where we're at principal stresses. Again, a reminder of what that means. When we're at principal stresses, all the stresses on the element are normal. There'll be a sigma 1, which is always our greater stress. You can see here the equation above says sigma 1 and sigma 2 instead of sigma x and sigma y, because these are specific stresses. Sigma 1 is always our normal stress that's greatest magnitude, and sigma 2 is going to be our, whichever of the normal stresses has less magnitude. And again, when we get to Mohr's circle, that becomes really visually apparent. And this is the actual numeric value, not just the magnitude. I think I just said magnitude here. But for example, if you had a negative 100 megapascals, so if you have 100 megapascals of compressive tensile force and you had just 5 megapascals of tensile force, the tensile force of 5 megapascal is going to be your sigma 1, even though sigma 2 is 100 megapascals of compressive force. So it's the actual value of the numeric value of the stress, not just the magnitude of it. Okay, so let's just start plugging some numbers in here, and as we work through this problem, hopefully this will all make sense. Okay, so using our sign convention again, looks like in each of these equations, the values we need to plug in are sigma x, sigma y, and tau xy. So up here, sigma x, so that's in this direction, that's 80 megapascals, but in the compressive, so it's negative. So sigma x equals negative 80 megapascals. Sigma y equals 60 megapascals. And tau xy is in the negative direction, negative 40 megapascals. Okay, so let's just start plugging things in. And it doesn't matter hugely which order we do it in. We could either find our angle, the orientation first if we wanted to do that, or we could go and find the magnitude of sigma 1 or sigma 2 first. Either way will work just fine. So let's go ahead and let's just start plugging in for sigma 1, sigma 2. So you can see here there's two terms. First one is the two normal stresses added together divided by 2, and then the second term is plus or minus the value of this one. And just a little preview of what's coming too, if you think back to your trig class or geometry class, maybe you're recognizing a little bit that this equation looks like the equation for a circle. Again, a little prelude to Mohr's circle coming up. This component here of the equation would be the center point of the circle along the x-axis, and then this square root of 2 terms squared, that's going to be the radius of the circle. Okay, so let's go ahead and sigma 1 would be equal to sigma x plus sigma y, so minus 80 plus 60 divided by 2. So minus 80 plus 60, that's going to be 20 divided by 2, so that component is 10. And then plus and minus the square root of negative 80 minus 60 divided by 2 squared plus negative 40 squared. So this one, negative 80 minus 60, so that's negative 140 divided by 2, that's negative 70 squared, so that's not something I can do in my head. So let's come up with an answer in the calculator. Negative 80 minus 60 divided by 2 squared plus negative 40 squared, 6,500 square root of that equals 80. So plus and minus 80.623. Okay, so sigma 1 then equals 10 plus 80.623. So it's going to be equal to 90.623 megapascals. Sigma 2 equals 10. Oh, you know, looking back, there was a negative in front of that I missed. Negative 10. So this is negative 10. So really this is 70.623. And sigma 2 then would be negative 10 minus 80.623 equals negative 90.623 megapascals. So those are our two principal stresses. And you can see sigma 1 is always the greater one, so it's 70.623 megapascals of tension. Sigma 2 is going to be negative 90.623 megapascals, so that would be 90 megapascals of compression. But we still don't know what the orientation of those are compared to our original orientation here. So I need to figure that out, and I can do that using this equation that has the unknown theta p that I need to rotate through. So in that case, rearranging that, I'm going to have 2 times theta p is equal to tau xy. That was negative 40 over sigma x minus sigma y, so minus 80 minus 60 divided by 2. Oh, I forgot the tan to the negative 1 in front of that all. Okay, so negative 40 divided by, well, let's do it the other way. Get that one, negative 80 minus 60 divided by 2, negative 40 divided by that, inverse tangent of that. So we get that 2 of the angle we need to rotate through is equal to 29.745 degrees. So the actual angle we rotate through would be half of that. So divided by 2 equals 14.872 degrees. So that and it's a positive number. So that tells me if I come back and think of this orientation up here, where I have x and y along this, to get to my principal stresses, positive angle, I'm rotating this way, I'm going to rotate that up by, this would be my new x prime rotated to my principal stress would be at an angle of 14.872 or 872 degrees. Okay, so we found our principal stresses, sigma 1, sigma 2 here. We found the angle we need to rotate them to, so we can summarize that. I guess one thing what we haven't done yet, though, is we know that one of these principal stresses is on this incline of 14.872 degrees, but I don't know which one of those it is yet. So I know that I know the magnitudes of them, and I know that one of them is at this 14.872 degrees, and I know that the other one, they're always orthogonal to each other, right? Our normal stresses, one of them is whatever angle we're looking at, the other one's going to be at 90 degrees to it. So I can figure out what the other one is, but I don't know which of those it's going to be at. So to clarify that, I need to go back and use my equation. Where's our sheet here? We have this equation here, right, that lets us plug in our unrotated stresses and some angle, and it will give us the value on that rotated one. So if I plug in 14.872 degrees into this equation, I will come up with either 70.623 or negative 90 megapascals. And that's how I'll know which one is on if it's sigma 1 that's at this 14.872, or if sigma 1 is 90 degrees away from that. So we'll go ahead and use that equation and plug them in. So again, let's see if I can get it to where we can see both those here right now. We're going to be using this equation for normal stress on any arbitrary plane, and we're going to use our 14.872 for it. Okay, so the equation is sigma x prime is equal to sigma x, so in our case that's minus 80, plus sigma y, that's 60, divided by 2, plus sigma x, that's negative 80, minus 60, divided by 2, times cosine of 2 times the angle we're looking to rotate, which in this case that's 14.872 degrees, and then plus tau xy, which was negative 40, times sine of 2 times 14.872 degrees. Okay, so we can plug all that in now. Negative 80 plus 60, we already did this one, divided by 2, so that's minus 10, plus negative 80 minus 60, divided by 2, times cosine of 2 times 14.872. So this piece is minus 60.778 plus negative 40 times sine 2 times 14.872. That's negative 19.845. Okay, add those three components together. Negative 19.845 minus 60.778 minus 10. And we get negative 90.623 degree, or 623 megapascals. Okay, and I said that it better turn out to be one of our normal stresses, and it is. It's sigma 2. So we now know the orientation that if we rotate up by that 14.872 degrees, that is going to be our sigma 2. So we would have the 90 megapascals of compression. And our orthogonal nature of the normal stresses tells us that we know if we go another 90 degrees, then we would come up with 70.623. And we can do that just to prove that right now. We can say that sigma prime, we'll just call it y prime here, equals minus 80 plus 60 divided by 2 plus negative 80 minus 60 over 2 times cosine. And now let's do 2 times, and we'll add 90 to that, so that would be 104.872. And then plus negative 40 times sine times 2 times 104.872. Or I also could have subtracted 90 degrees. Again, right, that would just have been the opposite orientation. Those would be 180 degrees apart, which would be the same normal stress. So we know this piece is still going to be negative 10. This piece is going to change, negative 80 minus 60 divided by 2 times cosine 2 times 104.872. So this piece now is positive 60.778. And now this side, negative 40 times sine 2 times 104.872. This is 19.845. So we add those three together, plus 60.778 minus 10. We get equals 70.623 MPa. So it does check out. Again, that was what we came up with for our sigma 1, our principal stress number 1. So we've done it. We've figured out our orientation of them, the magnitudes of them. So let's just summarize that. Sigma 1 equals 70.6 megapascals. And theta to get there, theta sigma 1 equals 104.87 degrees. Sigma 2 is a negative 90, so 90.6 megapascals compression. And the angle we have to rotate to get there is just 14.872 degrees. So that gives us our principal stresses. And you may be asking, what's the shear stress there? And again, just as a reminder, there's no shear stress when we're oriented at the when we've rotated our axis to the point where we're at principal stresses. That means all of the stress in the element at that orientation is only normal stress. There is no shear stress. So let's look though, let's find the maximum in-plane shear stress. So we can do that using these equations down below. Two separate equations now. One is for the max in-plane shear stress, that's this piece right here, and the other is for the average normal stress. And you remember, I think I talked about this at the intro to this video. Just like when we're at the principal stresses, if we rotate to principal stresses, there's zero shear stress. If we rotate to where we're at max in-plane shear stress, that means the normal stresses at that orientation are equal to each other. So your sigma x and sigma y will both be the same magnitude and the same direction there. Okay, so let's go ahead and we could plug in values for these, but there's a reason that I did the principal stresses first when I was solving. If you look at the equation for the max in-plane shear stress, it's equal to the square root of sigma x plus sigma y divided by 2 squared plus tau xy squared. Looking back up here, that looks a lot like that piece of the principal stress equation, doesn't it? That's that term right there. Looking at the next equation, the equation for average normal stress at the orientation for max in-plane shear stress, that's identical to the first half here. So if you solve this piece first, you've already got the numbers you need for solving for max in-plane shear stress. So I'll just say from above, max in-plane shear stress is equal to, we found that the value for that term was 80.623. 80.623 megapascals, and sigma average is equal to, that's this term, which was the same as up there. That's going to be equal to, plugged in value, that was negative 10 megapascals. So that tells us that when we've rotated our element to the point where we're at max in-plane shear stress, the shear stress will be 80.623 megapascals, and the average normal stress will be negative 10 megapascals. So in both the angles perpendicular to that, we'll have a compressive stress of 10 megapascals will be what that element is feeling in that orientation. Okay, we're not quite done yet. We haven't figured out the orientation of this, how much we need to rotate to get to max in-plane shear stress. I will give you a hint though that the max in-plane shear stress is always 45 degrees off of the principal stress on the real world element. So my guess is that our two angles here were 14.872 and 104.87 degrees there. Our shear stress should be right in the middle of those two, but let's go ahead and solve for it to find out. So using this equation here, we can plug in values and we'll end up with 2 theta s, move up here, is equal to the inverse tangent of negative, again, don't miss that negative sign there, negative sigma x is minus 80 minus 60, that divided by 2 over tau xy was negative 40. Okay, so if I plug all that in, let's start negative 80 minus 60 divided by 2 divided by negative 40 times negative 1, inverse tangent of that. You get 2 theta s is equal to 60.255. Sorry, that's negative 60.255 degrees. So divide that by 2, and theta s equals negative 30.128 degrees. Okay, so let's think about that. It's saying negative 30 degrees, so up here we rotated positive 14.872, and now we came up with a negative 30.128. If we take that negative 30, so I'll just write that out here a little more clearly. So our theta s, the amount we need to rotate to get to our orientation we'll have max in-plane shear, is negative 30.128 degrees. We could have also rotated the other direction, but let's just look at the difference between what we found for our principal stress here of 14.872 degrees. If you look at those two numbers, hopefully you're kind of seeing those look. If we add those together, we're probably going to get 45 degrees. So let's say just take minus 14.872 just to get the magnitude right. And yeah, that's 45 degrees. So this just shows us that the max in-plane shear stress is always on an orientation that's located 45 degrees off of the principal stresses. And again, when we get into Mohr's circle, all of that becomes really clear visually. But to summarize this last part here where we're looking at max in-plane shear stress, tau max in plane equals 80.6 megapascals. At that orientation, the normal stress will be same in the x and y perpendicular to that, so that would be average is going to be equal to negative 10 megapascals, or 10 megapascals of compression. And to get to this orientation, we have to rotate by negative 30.128 degrees. And we just talked about how that's 45 degrees off of our principal stress that we found. Okay, our next step is to look at Mohr's circle to bring all these pieces together of finding the stress on any arbitrary plane, finding the max shear stress, the principal stresses, etc. Okay, so far we've gone over 3 different methods of doing stress transformations. We started out using the equations of equilibrium on a free body diagram. Let's see, that was back on this one here. You can always fall back to that, but as we found out by doing that, that's fairly tedious because of all the transformations of each individual known force into its components along the rotated axes. And once you've done it for one rotation, you have to do the whole process again if you want to find out at any other angle. So pretty time consuming. Then we also looked at the general stress transformation equations that take this concept and use trig identities to develop equations that can lead us straight to sigma prime and tau prime. So that's these 3 equations here that we used. You can find the rotated stresses or the transformed stresses at any arbitrary plane of angle of rotation. Then we looked at a couple special cases of that. The principal stress case, that's where all stresses on the original orientation have been transformed into purely normal stresses. So basically all the shear stresses are now contributing to normal stresses. And we talked about how that will end up, there'll be one that's the larger normal stress, that's our sigma 1, and then the smaller one would be sigma 2. We also talked about at a orientation located 45 degrees of rotation away from our principal stresses, we have our location of max in-plane shear stress. And when we have max in-plane shear stress, we're going to have the average normal stress at that location. So we used these equations down here to find max shear stress in plane, and then the average normal stress at that. So what we're going to look at now is the Mohr's circle method. And Mohr's circle is a great way that kind of puts together all of the pieces that we've just worked on in a graphical method. And so before we actually do it, I just want to kind of review what is this whole stress transformation concept about again. So we're going to use the same problem that we've been working on so far on each of these methods. So that's with sigma along x direction being 80 megapascals of compression. On y direction, we're looking at 60 megapascals of tension. And then we had 40 megapascals of shear. And again, reviewing our sign convention, that 40 megapascals is negative shear because it's not moving up and to the right in our quadrant with positive x and positive y. Okay, so to start this problem, we were asked to find the state of stress on a plane, AB, that was at an angle of 50 degrees off of the horizontal. So another way of saying that is that plane's rotated 40 degrees this direction. That's our positive sign direction, is coming from x to y. So this angle right in here would be 40 degrees. And then we solved using our equations of equilibrium for the normal stress along this axis and then the shear stress along that axis. Then we looked at the principal stresses, and that's where I'm just using this kind of graphical image here. The location of the principal stress orientation is when we rotate this element in such a way that our new normal stresses, stress along x prime and y prime, are balanced. They basically, all of the original components, this 80 megapascal that originally was parallel to our x-axis, as we rotate this element, some of that 80 megapascals is now creating a normal stress along our x prime, y prime, and some of it's creating a shear stress. So as we rotate around, we'll end up at an orientation where all of this shear stress is now contributing purely to normal stresses, and that's our principal stress plane. And I can't remember, let's go back and look. We found out that our principal stress plane, and there's two of them, right? One would be our basically sigma x prime and one would be sigma y prime. One of them is at an angle of 14 degrees, 0.872. So that would be, here we are at our original orientation. We rotate this element to where it's up by 14 degrees, and that's going to be where we have one of our normal stresses. And then our other, or one of our principal stresses, and then our other principal stress would be at the rotation of 104.872, so 90 degrees away from that. Basically, one of them would be along our x prime, the other would be along the y prime. We also looked at, there's a different orientation where we rotate to such a point where we have an average normal stress. That means the normal stress is the same in both along x prime and y prime. And at that point, the shear stresses are maximum. And in this case, when we solved for that, we found that to get to that point, our rotation was a negative 30.128 degrees. So in this case, if we rotate our element that we're looking at minus 30 degrees, something around there, that's where our shear stresses will be at their maximum. And at that point, the normal stress along x prime and the normal stress along y prime will be equal. Okay, just kind of wanted to show again what the whole point of this is. We were given a stress state on some arbitrary pair of axes, x and y, and then if we want to find stress at other locations, we do that by rotating the little element and translating those forces from our original set of coordinates to our new set of coordinates. A couple special cases are where the principal stresses are and max in-plane shear stress. Okay, now that we've reviewed that, let's look at doing that same process but using Mohr's circle method. So Mohr's circle is a way of doing finding any the stress state at any angle of rotation, finding the principal stresses, finding max in-plane shear stresses, all in one kind of graphical method. So let's start out. We've got our same element that we've been working with all along here. One thing to talk about before we start solving this particular problem is just reviewing our sign convention, because there's one little tweak to the sign convention about Mohr's circle. So again, here's our original element. We were looking at stresses on a plane that was 50 degrees off of the horizontal. So to get to that, that means in reality we're rotating up 40 degrees. So our rotated axes here, just like in all our previous ones, was, let's see, I think x prime was fuchsia. So that if this is our x from our original over here, that's x is parallel to the 80 megapascals applied. Our x prime then is up here. So that would be x prime, and that angle in there would be 40 degrees, right? That's rotating in the positive direction 40 degrees. Okay, and then our y prime rotated now would be perpendicular to that, so another 90 degrees along, and this would be y prime. Okay, our new angle there, 40 degrees. It's a positive 40 degrees because it's moving in following the right hand rule. And other sign convention, we are now going to plot these stresses, the 80 megapascals, the 60 megapascals, and the 40 megapascals on this chart. And this chart on the x-axis are normal stresses, and on the y-axis are shear stresses. In the normal stress axis, our sign convention is just as you would expect. Positive is to the right. The oddball one is that to make the numbers work out correctly as we rotate around the circle, on our shear stress axis, negative shear stress is up, what we would consider positive y direction. So that's a little odd compared to our normal quadrant one up here. So positive shear stresses are plotted below the normal stress axis, negative shear stresses are plotted above. So looking at this particular problem, we had that on our x plane here, so looking at parallel to x, we had sigma x was equal to 80 megapascals of compression, so that would have been a negative 80. Sigma y, so the stress acting parallel to our original unrotated y-axis, that was 60 megapascals tension, so 60 megapascals tension is positive 60. And then the last one is tau about unrotated xy was equal to 40 megapascals, and it's not in the positive direction up here in our top right quadrant, so that's negative 40. So what we can do to start constructing our Mohr circle, and I'm going to show you how we would graph it without using any of the equations. You can do this, skip kind of thinking through what's going on behind it and just use these equations to plot Mohr circle, but I want to show you how we came up with those equations. You may recognize those equations back from when we were looking at our principal stresses. You can see sigma average and the radius of our circle are each a piece of the equation for sigma 1 and sigma 2. You can see that first term in the equation for sigma 1, sigma 2 is equal to sigma x plus sigma y divided by 2. You can see that's the same thing as the average normal stress. Okay, then looking at the second component there, you'll see that sigma x minus sigma y divided by 2, all that squared, plus tau xy squared, square root of that, that's the radius of the circle we're going to be drawing. And again, if you think back to, gave the kind of hint as we were looking at this originally back under our first lesson on principal stresses, this looks like the equation of a circle centered here with radius of this magnitude. Okay, so those equations are there. We'll come back and talk about those in a minute, but I'm going to show you that you actually don't even need those equations. You can derive those from the graphical circle itself. Okay, so our first state of stress, let's look at the 80 megapascals. That was parallel to the original x axis, and it was minus 80. So if we're looking along normal stresses, we have a negative 80. So it's going to be somewhere along this line here, negative 80. So I'm just going to kind of draw, it's on that line. And then at that same orientation, we also had a shear stress of negative 40. And again, here's the tricky part. Remember, negative shear stresses are upward, so that would be in line with this. So if I'm going to plot the stress state at the original orientation along the x-axis there, that's 80, a negative 80, and negative 40. So right there. That point is negative 80 normal stress, negative 40 shear stress. So that's one of the two points I know about the shear state. I also know that in an orientation rotated 90 degrees in the real world, I also have another stress state that was given to me of 60 megapascals normal stress. So 60 megapascals normal, and this was positive, so I'd be moving to the right on the plane. So that's going to be somewhere along here. And once again, I have 40 megapascals of shear stress, right? The shear stress doesn't change at that from that one to the magnitude of it. So 60, and now I'm looking at 40 because I'm down there. So now I have 2 points on this. So this is 60, negative 40. Okay, so those are 2 points on my circle. So I can right now take a compass and guess I need to find the center where that circle is. I can either find the center of the circle using my sigma average, but let's look at how that where this equation came from. If I connect those 2 points that I've just plotted, that's basically the diameter of the circle, right? And so let's look at that on a kind of quantitative. The distance between those 2 points, this distance here, that is the distance between our 2 stresses, right, that we were given, the negative 80 and the 60. So this is where we get that equation for sigma average, which, as I mentioned, is also the center point of the circle. So in this case, this value over here is 60. This one's negative 80. So the distance between those would be 60 minus negative 80. That'd be 140. So from here to here is 140. And then divide that by 2, right, to get half of it, to find how far it is into the middle, equals 70. So the distance from either end here is 70. So that's basically sigma x plus sigma y divided by 2 is our normal stress. But I did it as far as actual distances. If you look at it, the way they did it here would have been, math-wise, sigma x was negative 80 plus sigma y was 60. So that's plus 60 equals 20 divided by 2. So that gets you straight to the actual numerical value of this right here, would be negative 10. So that's how we find where the center is right where it crosses there at negative 10. Okay, so we can take our compass here. And we've now drawn our Mohr's circle. Let's look a little bit more about what we know about the points on this circle. When we talked about principal stresses, the max in-plane shear stress, I talked about the principal stresses are the orientation where there's no shear stress on the element at that rotation. So as we look at this, let's think about where on Mohr's circle is there no shear stress? Well, we're measuring shear stress on the kind of vertical axis here. So the 2 principal stresses, that's the location where there's 0 shear stress, one of them would be right here, and one of them would be right here. That, again, if you look at that, that's no shear stress. One's a max normal stress, so this is sigma 1. We talked about sigma 1 is always the greater of the 2 normal stresses, or 2 principal stresses, and this one would be sigma 2, because it's the lesser one. And this is a good example where I talked about it's the actual numeric value of it, not the magnitude necessarily. So sigma 1, we can see here, looks like just graphically is going to be about 70 megapascals. Sigma 2 is about negative 90 megapascals. And again, if we come back to where we used our equations, that looks like what we had here, right? Is 70 megapascals of tension for sigma 1, 90 megapascals of compression for sigma 2. Okay, let's talk about max in-plane shear stress. So the maximum shear stress would be where we're furthest along the vertical axis here. Looks like that's just a little bit over 80 and just a little bit over 80 there too. If we come back and look at max in-plane shear stress, looks like we were just about 81 megapascals. So that's kind of helping us see these points. So this point up here, right there, that is the location of tau max in plane. The other thing we talked about when we were looking at the max in-plane shear stress, at that location, at that orientation, when we've rotated our element to that point, we said that the normal stress there would be equal to the average normal stress. And when we did that by equations, we came out to negative 10 megapascals. And that's basically where we intercept this normal stress axis here, right? That's negative 10. We solved for that right up here in one way. Okay, so that's kind of talking through graphically what we can see on this circle here. And again, we have plotted out the stress state at the one orientation we were given. If we want to answer questions about other orientations, we can do that using trig here. Let's talk about what we know trig-wise about this circle. We pointed out how we found this center point of the circle. That's basically the average stress by figuring out where's the midpoint between our two normal stresses. But hopefully you can kind of see that this is a right angle right here, right? A right angle triangle that we know all the parameters of. So if we redrew that triangle out here a little bit, and you don't need to do this normally when you're solving the actual Mohr circle, but I want to kind of make it clear what we're looking at here. So we've got our triangle representing this one in here that I've just brought out to make it a little more clear what we're looking at. And let's talk about what we know about the geometry of this triangle. Again, when we started out to find the center of this circle, we did that by looking at the difference between our first normal stress, the negative 80, and the 60. And by subtracting, actually by adding the magnitude of those together and dividing by 2, we found our center. So we can see that the distance from here to here, as far as numbers, right, it's from 80, the basically normal stress component, negative 80 back to negative 10. So as far as numerically, this distance is 70. But the way we found that, if we didn't already have those numbers plotted out, if you're looking at the triangle, or the whole circle really, that value would be sigma x, that's negative 80, minus sigma y, that would be the 6, or I wrote it out there, that's our 60, but sigma y divided by 2, right? In this case, that would have been negative 80 minus 140, or minus 60 would get me negative 140 divided by 2, so the answer then would be negative 70. That's the distance there. Magnitude's really all I care about of that, right? 70 on this triangle. Okay, looking at this piece here, the height of that triangle is just the magnitude of the shear stress at that point. It would be the same as the height right here, right? These are the same triangles, just from different side. So this side is equal to, for us, 40, or if you're thinking about it as a variable, that's tau xy, the unrotated shear stress. So if we want to know anything about the triangle, we've got two sides basically. We can find the angle, we can find the radius, and let's look at that. And I'm labeling that as r instead of the hypotenuse because that is what this circle is, or what that side is, right? It's the radius of our Mohr's circle. So hopefully you're starting to see we're starting to look a lot like this equation up here. If we want to solve for r, if you know that r squared equals the a squared plus b squared, right? And in this case, a squared could be, so let's just rewrite that in terms of r. R is equal to the square root of, we'll use a as this bottom side, sigma x minus sigma y divided by 2, all of that squared, plus tau xy squared. And again, that's the same thing as our equation up here for the radius. So you can see how we're developing each of these pieces, how we can find the average, the center of the circle. We already talked about that. And now we've shown how to find the radius. So I drew out the circle just based on plotting those 2 points. I could have gone straight to finding the radius without drawing these points and, and the center by using sigma average and just found my center, set my compass to my radius, and drawn the circle. And then I could have labeled the 2 points I knew, -80 and -40, and 60, 40. So that is kind of the trig that's going on behind there. So let's plug in a value for this, for each of these. So for radius is going to be equal to, and this would be the square root of, we already found this out, sigma x minus sigma y, that is -80 minus 60, so -140 divided by 2. So that's going to be 70 squared. Well, it's -70 squared. And then tau xy was -40, so plus -40 squared. Let's see what that comes out to. 70 squared is 40 squared, square root of that. So I get that R is equal to 80.62 megapascals. And I think that's similar to what we found out before, wasn't it? Yeah, basically, that's the same as the max in-plane shear stress, right? Radius would be this location where we're coming purely up or purely down. That would be our max shear stress. So it looks like our R doing this formula works out just the same as when we did the general stress transformation for principal and max in-plane shear stress. Okay, so that's one useful information. The other one that we've kind of done just graphically but didn't actually solve for yet was the sigma average point. So we can write that one out. Sigma average equals sigma x plus sigma y. So basically we're looking at this here again divided by 2. So that was -80 plus 60 divided by 2. So that's -20 divided by 2, so it's -10 megapascals. And that's just proving what we already did here graphically, that the center of the circle, which is the average normal stress, that's the amount of normal stress when we're at our rotation for max in-plane shear, is going to be equal to -10 megapascals. So right here, we just figured out the state of stress for our max shear orientation, but we haven't proved where that is as far as rotating our original block. So let's think about how we would do that. That point is going to be on the Mohr circle is here or here, right? So if we can do it either by coming back, rotating clockwise from the one point that we do know, or we can rotate forward. And actually we still have a lot of information that we can find from the circle, but let's go ahead and find the plane of maximum in-plane shear stress down here, since we've kind of started working towards that one. So if you remember back, we have an equation that does that. It's tan 2 theta s sigma x minus sigma y divided by 2 tau xy. So we've solved that previously. Let's see what happens if we do the same thing using Mohr's circle, what we end up with. So a couple things to talk about Mohr's circle and when we're looking at angles. If you look at Mohr's circle, you can see that sigma 1 and sigma 2 are located 180 degrees apart from each other on Mohr's circle. Thinking about what they represent, we know that in real life, the normal stresses are always 90 degrees apart from each other. So Mohr's circle, any angle that you measure on Mohr's circle is twice what the angle is in the real life. Let's think about that, what I'm saying. We know that in the state of stress that we were given, -80, -40, and 60, 40, those axes are 90 degrees apart from each other, right? Let me move down here. Those axes, that's our x-axis is the one with the -80, -40, and our y-axis had the 60, 40. So those in real life are located 90 degrees apart from each other. On Mohr's circle, they're 180 degrees around the circle from each other. So that's just a rule about how Mohr's circle works. You move twice as far on Mohr's circle as you do in the real world orientation. Okay, so just getting that out of the way, now we can look at how far would we need to go. So let's go ahead and find what we would need to rotate to get to this max shear stress up here. And again, there's two planes for that, right? we have max shear stress up here and up here. We're going to work back to this one, but know that in reality, that plane is going to be located 180 degrees around the circle from this one, which is just 90 degrees in the real world. Okay, so let's find that. How can we find that? We know information about this line right here, right? We know that we just found out the height of this triangle, the base of this triangle, so we can solve for this angle in here. And let's call that angle, why don't we call this one phi? So using our basic trig, we know that the tangent, let's just move over here, tangent of phi is going to be equal to the opposite, so it'll be equal to 40 over the adjacent over 70. So that's our solving for that angle there. So if we plug that in inverse tang, let's see that phi is going to be equal to 4 divided by 7. So that tells me that phi is equal to 29.745 degrees. So that angle right here, this is phi. Okay, so we know something from the horizontal axis to our state of stress that we were given along our original x prime. And now we're looking to find out the state of stress up here. So looking at that, we know that that state of stress is right there. So we want to find out what is the angle between these two. That's pretty easy now, right? We know that this is vertical, right? It's a 90-degree orientation. Our max shear stress is up here right above our average normal stress. So now let's call this one, let's call it gamma. So we know that gamma is going to be equal to 90 minus phi. So that's equal to 90 minus 29.745 degrees. So 90 minus 29.745 is equal to 60.255 degrees. That's gamma. That's the rotation from our original orientation, what we would need to rotate to get to a max shear stress. And let's pay attention to the direction of the angle. We've said that positive is moving from our x axis to y. So this direction, moving from x towards our y, right? X had the negative 80, y had the 60. So if we went this way, that would be positive. We're going the opposite way. So in this case, if we're keeping track of our directions, gamma equals negative 60.255 degrees as far as our angular sign convention. Okay, we've said that if we rotate 60 degrees in the real world, in Mohr's circle, we're going to be half that in the real world. So the amount that we would actually need to rotate our little element, if we had, I don't know where I had my little green card that I was using to show that, but we would be rotating backwards this amount, half that amount. So divided by 2. I accidentally divided by 2 twice. 60.255 divided by 2 equals 30.128 degrees. And if we come back here, looking at our equation-based one, that's what we came up with, right? Oh, I forgot to bring my negative sign forward. So we would rotate in a clockwise direction, that's the negative direction, 30.128 degrees to find our orientation where the shear stress is maximum in plane. Okay, that's one useful piece of information for us. And we already figured out the magnitude of that, right? That's just going to be the 80.62 megapascals. Okay. What other information? Oh, let's find our principal stresses. So we've said that principal stress 1 is out here, principal stress 2 is back here. We've got most of what we need to figure that out, I think, right now, don't we? We know that the center of the circle is at negative 10 megapascals, and we know that the radius of the circle is 80.62. So in this case, it's real easy to find our principal stresses. Principal stress 1 is equal to sigma average, that's the center of the circle, plus our radius, right? And sigma 2 is going to be equal to sigma average minus the radius. So sigma 1, basically we go from here, add the radius to get to there. For sigma 2, we start at the center, that's sigma average, and we go to the radius the opposite direction. That gets us this one here. And we've got both those values already, right? Sigma average was equal to, so this is equal to negative 10 plus the radius of 80.62. So sigma 1 is going to be equal to 70.62 megapascals. Positive, so that means it's tension. And sigma 2 is negative 10, that's the center, minus the radius, so minus 80.62. That's going to be equal to negative 90.62 megapascals. So that tells me that's in compression. And again, if we come back and look at our answers from before, we had 70.6 megapascals tension for sigma 1, 90.6 megapascals compression for sigma 2. So we're doing great on those, but we haven't, well, I guess actually we did already find what orientation we needed to rotate for one of those. We did it as part of finding the rotation for our in-plane shear stress, right? Looking back at our triangle here, we can see that to get down to our sigma 2 principal stress, we would be rotating, following right-hand rule, that's a positive rotation, and it would be equal to our phi on Mohr's circle, or it'll be phi divided by 2 in the real world. So we already solved for phi was equal to 29.745. So the angle we need to rotate to get to our principal plane 2 would be equal to phi divided by 2. In this case, that's 29.745 degrees divided by 2 equals, so 29.745 divided by 2, that's equal to 14.8725. We'll just leave 87 degrees. 14.87 degrees. Let's look at what we calculated before. Yep, to get to sigma 2, we got there before at 14.872. And now here's one thing to notice. When we did this, when we did it using the equations for finding the principal stresses, we found the magnitudes pretty quickly, but we had to go through a second step to find the angles to figure out which one of those principal stresses was at an angle of 14.872, and then we figured out the other one was rotated another 90 degrees beyond that at 104.872. Whereas when we're looking at it doing Mohr's circle, we can tell immediately, am I looking at sigma 1 or sigma 2 in this case? So just verifying what we did using the equations. So we found that sigma 2 is at an angle of 14.87. Sigma 1 is going to be another 180 degrees around the circle, which is 90 degrees in the real world. So that would be 90 plus 14.87. So again, we come up with 104.87 for sigma 1 as far as our orientation. So far now we have figured out, I'll just write these out, that's sigma 1, that's sigma 2, this is angle to the plane of sigma 1, and we can, that's sigma 2, rotation to get to sigma 1 is equal to 14.87 degrees plus 90 degrees. So that's equal to 104.87 degrees. Okay, so we've now found all of our principal stresses and their orientations. That's that part. We found our max in-plane shear stress. That is right here, basically. I didn't label it clearly, so let's label that one down here. That tau max in plane. We found that by just looking at the radius, right? The radius is going to be where we're at our highest shear stress, so that's equal to 80.62 megapascals. And the orientation to get there, we found that back here by figuring out what gamma was and dividing it by 2. So that's this angle right here, max. So we'll call that shear is equal to negative 30.128 degrees. Okay. So I when we were doing the Mohr circle version of this problem that we've done 3 different ways now, I went straight to finding principal stresses and normal stresses. But you'll remember we were actually asked when we started this problem, we were trying to find out the state of stress on an element rotated 50 degrees off of the horizontal, or as we talked about, that's 50 degrees off of the vertical on this side. So that's our x prime being rotated 40 degrees. We haven't solved that question yet using Mohr's circle. So let's look at that. Again, in the real world, the element rotated 40 degrees in the positive direction. So on Mohr's circle, we know that means we're going to be rotating 80 degrees around Mohr's circle and in the same direction. So if we were going from x to y, so that's positive, that means we're going from, this is our x, right? Then 80, and we're moving towards y. So we're rotating about the circle in this direction. It's going to be a little less than a 90-degree angle. So I'm just going to kind of show it out here graphically before we actually find numbers for it. So basically, I'm looking for this point here, and we'll label that as point AB because that's the plane that we were looking for back up on the original question. So we need to figure out the coordinates of that to find out the normal stress and the shear stress at point AB. And hopefully you're starting to see how we can do that. We know what the angle is between these, right? It's twice the rotation in the real world. So if we rotated 40 degrees here, this angle is 80 degrees. Okay, so we already knew what this part here was. Sorry. So it's just going to be right angle trig again. This is 80 degrees. This was, that's our phi was equal to 29.745. So let's call this one down here, I don't know, I'll call it nu. So to find the value of that, our little nu is equal to 80 degrees. That's the angle between our given original state and our rotated state. And it's 80 degrees because that's twice the rotation in the real world. So 80 degrees minus, this one was 29.745. Oops. Okay, so 80 divided by 29.745, not divided, minus 80 minus 29.745. So that's 50.255 degrees. Okay, so we're just now we know what this angle is in here. So again, that's just a right triangle right there, right? This is the triangle we need to solve now to find the rotation at AB. So I'm running out of room on my paper here. I'll draw it kind of small. We're working on the triangle. We've now got the angle in here is equal to 50.255 degrees. We know the radius of the triangle, right? The radius is unchanged anywhere around here. That's the distance from the center of our circle out to the edge at any point. That's going to be, we found that was 80.62 megapascals. So we just need to find this length from here to here and the height from here to here. So we can do that using our trig pretty easy. This is our opposite, right? This is our adjacent. So 80, so let's do adjacent first. Adjacent is equal to 80.62 megapascals times adjacent would be cosine 50.255 degrees. Opposite is equal to 80.62 80.62 megapascals times sine of 50.255. So let's figure out what those values are. So for A, 80.62 times cosine 50, nope, not 50, 50.255. That is equal to 51.55 basically. And for the opposite, 80.62 times sine of 50, that is 61.76 basically. Oh, I forgot the 50.255 again. Sorry about that. Redo that one. 80.62 times sine of 50.255. There we go. That number rings more true from our other ones. 61.99 basically. Okay, so we're almost done. The one thing that sometimes students forget right here is what we just found is the properties of that triangle, but the center, the edge of that triangle is not at 0, 0. So the height we found for O, that is the value for max, or for the shear stress at that location, right? That's the distance from the normal stress axis down to AB. So this one is good as it is, but you'll notice as we move along the normal stress axis, we started at a point of -10. So if we're going to find the actual value for this distance right here along the normal stress axis, that's going to be equal to, so normal stress AB equals -10, and then we're going in the negative direction. So we start here and then go minus what we just found, that minus 51.55. So our normal stress is going to be equal to negative 61.55 megapascals. And our shear stress at AB is just this height right here. And we solve for that directly of 61.99 megapascals. And if we go back and check what we had before, oh, that's not on that one. Let's find one of those ones. So we had normal stress of 61.5 and shear stress of 62. And the normal stress was compression. That's why we have the negative here. So it looks like we've come up with the same answers again for sigma AB and tau AB. Sorry, kind of ran out of room here at the bottom of the page, but hopefully that makes sense. And now the great thing about the Mohr circle method is you can see we found all of those different pieces. We found a arbitrary rotated set of stresses. We found our principal stresses. We found our max in-plane shear stress and the orientation of all of those. And now if we wanted to find the state of stress at any other plane, we could do that using the circle. We don't have to start over. We get down, once we have the radius and the center point, it becomes real easy to find the stresses at any location on the circle. Say we wanted to find out what the stress was over here. We know where our center is. We just draw a new triangle there, and we can solve for what the shear stress would be here. That would be this height right here. And what the normal stress would be, that would be this distance right here. And again, without even solving those numbers, we can look at this point and say, okay, at this orientation, it's going to be in tension because my normal stress is positive. And as I rotate around, I can get to a point where both of my stresses, both my normal stresses, remember they're always located 180 degrees across from each other on the circle. When we're at this point right here, you can see that they're equal to each other. And that's, again, a nice way to remember that when you're looking at max shear stress, here and here, you're looking at the average normal stress. And in this case, when we're at that orientation, we're looking at -10. So we have 10 megapascals of compressive normal stress when we have max shear stress. Okay, I think that's probably enough talking about Mohr's circle. Hope that's helpful.